Hi everyone, I'm Zhou from University of Chinese Academy of Science. Now I'm presenting our recent work about firmware emulation. This is a joint work covered by UCAS with UGA and Penn State. Nowadays, microcontroller has been widely used in embedded devices, such as in digital control and smart medical. However, there's an increasing number of MCU vulnerabilities has been reported recently. For example, taking advantage of the bug in plant equipment, the attacker can force shut down the furnace. Furthermore, the bugs in a medical device will directly endanger patient life. Therefore, bug finding in MCU-based device is very important. And as we all know, the dynamic analysis is popular in bug finding, like tender analyze, sample execution, and especially for the fuzzing test. However, we found that this exciting approach cannot be directly used for MCU firmware. Dynamic analyze either runs a target on the actual environment or emulator. However, the real hardware does not provide rich real-time information, like feedback of coverage and the crash signals, which are very important to fuzzing test. Furthermore, on-device fuzzing test speed is also very slow. However, on the other hand, emulating entire firmware is also extremely challenging due to the diversity of the peripherals. So, to solve these problems, many solutions have been proposed. At first, research tried to emulate individual peripheral hardware with soft components. However, as we mentioned before, it is impossible to emulate all kinds of peripherals. Besides, such an approach requires significant manual effort to aid new peripheral hardware. Then, some researchers propose hardware-in-the-loop solution, which do not emulate peripheral function, but forward the interaction with the peripheral to the real hardware. However, such approach still requires real hardware, and the testing speed is very slow and unscalable. The third type of emulation is replacing hardware abstraction layer with software stubs. However, the fourth limitation is the peripheral-dependent code will be skipped from analyze. In addition, some developer may directly invoke driver functions without abstract interface. So hardware abstraction layer does not always agreeable for all firmware. Currently, the proposing solution is to build automatic peripheral model with firmware execution to achieve general full system emulation. For example, P2IM categorize the peripheral register based on access pattern and build a peripheral model based on register category. However, such approach also have obvious drawbacks. First, categorize the peripheral register based on access pattern is not very accurate, especially for some complicated peripherals. And miscalculation could lead to emulation failed. Second, the register calculator cannot be directly used to infer peripheral access. So P2M has to use heuristics to blending guide some register response, which also could crash or haunt the emulation. Therefore, we propose a new peripheral modeling approach with less heuristics and higher accuracy. Our approach are based on two key observations of peripheral usage. First, we found if we feed the wrong response to the firmware, the error will be reflected as an invalid execution state, like invalid loop. Also, the invalid execution state is directly reflected on an invalid path. As shown in the figure, the red path should be an invalid path, and the green path is the correct one. Second, we also found a response can be reused when the same peripheral is accessed again under the same context. Therefore, we propose to reply the peripheral access as a symbolic value. Through symbolic execution, we avoid the invalid path and so can learn the constraint certification-based value of valid path. Then we cache these values with contact information into a knowledge base. With the help of this knowledge base, we can achieve peripheral emulation without hardware-dependent and blending guides. These are our defined common invalid states during firmware execution, including infinite loop, long loop, and invalid memory access. Optionally, we also provide an interface for user to aid the invalid program prompts to be avoided. Based on invalid state detections, we can learn the correct value of valid paths. Then we use execution context to match this cache value. To capture both simple and complicated behavior of peripherals, our tool uses a tiered cache system. For example, use the T0 caching rule, it responds with the last return value. If the simple rule like T0 and T1 rule leads execution to invalid path again, it will automatically upgrade to the higher caching rule, like T2 and T3, which will include more front-grade context information, like function arguments and reading order. Now, to clearly show our approach, I show a running example of our tool. First, we symbolically execute the firmware to generate a knowledge base. In this example, we assume the left side green branch target is selected at first. Then the solver calculates a value that leads execution to this green path, and record it with the peripheral address and PC as the first entry in the trace1 KB. Along the trace1, we detect the execution state is invalid. Therefore, the execution switch to the blue trace2. Correspondingly, the first entry with 0 value is generated in current trace2 KB. Along the trace2, the firmware reads the same register and same PC again, so we return 0 value from trace2 KB, and the left blue branch target will be selected. However, we found the executions is invalid again, so the execution will switch to the red path trace3, and the default value of trace3 should be used, which will conflict with the original entry value 0. Therefore, we should upgrade the caching rules from the T1 to the T2. T2 rule applies more execution context. So the different value of T2 are created, one for each branch target selection. And after the knowledge extraction is finished, the KB of current red trace will be outputted. Now we can use this KB with firmware emulation. According to the different execution context, KB return different values to prevent the execution from the invalid states. So we realize our implementation on the S2E. S2E supports full system dynamic symbolic executions and provide useful plugins and APIs for ours. However, current S2E does not provide ARM support. So we first port the QEMU AMDBT to the S2E for CPU emulation, and we generate events that are used for S2E plugin firmware. The second task is to make emulate ARM CPU manageable with the KVM interface. We add several ARM-specific KVM interface, including register initialization, memory rejection, and system peripheral state synchronization. Then we can develop our plugin to implement the designed functions, including invalid state detections, knowledge-based extractions, and interrupt control plugin for interrupt interjection. To demonstrate the emulation capabilities, we also add a plugin for further integration. We use AFL as a drop-in fuzzer for test case generations and give the rest for our plugin, including coverage instrument for servers and crash and haunt detection. Then we can feed the test kit generated by AFL into firmware with data register, and other peripheral access will be handled by our knowledge base. Finally, to prove our tool is able to emulate the behavior of a wide range of peripherals correctly, we reuse the same firmware samples in the P2M experiment, which cover popular used peripheral MCU and OS. For each unit test, we first generate the knowledge base. During dynamic analysis, we monitor whether its output and execution flow as expected. As a result, for all tested samples, only 3 unit tests failed, which is much higher the result in P2M. Furthermore, with a little manual assistance like adding 1 or 2 invalid program paths, all unit paths can be passed. Then we also fuzzing test the real-world firmware. To comprehensively evaluate our work, we reused the 14 firmware in the other works, including P2IM, Holosimeter, and Pretender. We also create additional 6 for other computer real device, like GPS and 3 Pretender. For each sample, we also first run around a knowledge-based iteration and then start fuzzing for more than 1 day. First, basic block coverage will trail up to nearly 19%. Compared to the qEmu, which does not emulate any peripheral, the coverage improvement is significant, from 10 times to nearly 100 times. As a fuzzy result, we reproduce known bugs in previous work. Furthermore, we also detect 2 unique peripheral unknown bugs. After manual verification, there are some false cross and harm due to lack of DMA support. So note that currently our prototype is limited to the fuzzy test. In the future, we will explore other dynamic approach on the top of UEMU, such as tend analyze, and we also try to integrate ARM support tool on the top of the UEMU. Now, as summarize our work, we present µEmu, a dynamic analysis platform with capability to emulate firmware for unknown peripherals. We developed it on the top of S2E using plugin and 8 ARM support. We demonstrate emulation capabilities with fuzzing tests of real-world firmware and found some previously unknown vulnerabilities. Our tool has also already open sourced at GitHub and welcome to use. Thanks for attention, and I'm happy to take any questions.